That's better. Okay, welcome to Analysis 220. I'm happy to see some familiar faces. I hope they are happy to see me. Thank you. Okay, so we've got a nice group. I'm glad to see we're fitting into the venue. I was a little worried, but it all looks good. Right? And I trust you all have gotten a study guide. Anybody still missing a study guide? Come and get one from me afterwards, please. Okay. Textbook. Right? I'll give you the name just now to double check, but please make sure to get a textbook, not only for good reading, but also almost all the exercises we're going to be doing in this course will be from the textbook. Okay. Okay, so, anybody do the suggested reading? Did you see that there was some suggested reading on ClickUp? Right, to get you going on analysis. Right, and we have a few other things we're trying, like a little podcast. Anybody listen to the podcast? Yes. Was it good? Okay, we'll see if we can keep that going. Right, we also have a nice virtual bulletin board called a Padlet, where you can go and share your ideas or thoughts about the course or ask a question. Right, so please engage with this course. And we can have fun. Let's see if anybody has submitted something. So I like to always start my lectures with a little question. Right, those of you who had me for first year calculus know this. There's a URL you can just put into your smartphone or your notebook or whatever. Right, you'll get to put up any answer you like. Or if you've got a smartphone, you can also just scan. I'm not planning to change this link. This will be the link we will have throughout. So you can always go to that one. Mark it a favorite if you like. Okay? The day before the lecture. So sometimes, right, 5 minutes isn't quite enough to have a good think on the question. Go, have a look at what the question will be, give it a think, and already submit your answer. Okay, let's see if there's anything. Yes? Okay, Biggs came home. What else do we have? Missed you. I missed you guys too. Okay. Great. And some soccer news alongside it, it seems. Okay, so that's the way we will usually start. Okay, I see we still have some stragglers coming in. Okay, I'm going to a scroll. Well, you're not first year anymore, so you should know where the venue is. That's no longer an excuse. So please try and be on time, otherwise you're going to miss the question, right? Okay, so let's get started then with today's lecture. Okay, so as you know, I'm Dr. Biggs. I'm not only your lecturer, but I'm also the course coordinator for 220. Right, so all your administrative queries will have to come to me. Right, and we will take care of that. Okay, textbook, right, is this one, Fundamentals of Mathematical Analysis, Haggerty. You might have one that's a little red, right? I see there are ones with different covers. Anybody have the textbook or have the red one? Can you show us the red one? There's a red one, right? So don't be worried if it's not black like this, it could be red like that. Okay, thank you. Okay, ClickUp, of course, you know, central resource for what's happening, right? So please go and have a look there. Study guide is there. I will also be posting all the lecture notes there. I am also experimenting with capturing the video and the audio, which is why I'm wearing 2 microphone clips. Okay, so hopefully if that works well, I will also upload a recording of what happens in lecture for you to go back to. Okay. Welcome. A few announcements. Okay. I want to remind you, please, you need to sign up for your lecture group, right, so that we can keep track who's where to help us. If we want to send an email to a lecture group or something like that, please sign up so that we have that. But even more importantly is you need to sign up for a tutorial group. Right, tutorials will start next week, and we will already have our first test next week. Okay, so be sure to go and sign up for a tutorial. How many here are actuarial students? Okay, I've got a lot of you. Right, unfortunately I see, correct me if I'm wrong, that the only slot that suits you is Wednesday 7:30. Ish. Yes, I will probably have to be there too. Okay. Now, unfortunately, that venue is already overbooked, right? And I see many of you have filled in the query form. So we're going to have to make a plan to get a bigger venue or get a second venue for that slot. So I will let you know, hopefully by the end of the week, how we've resolved that, right? So if you haven't signed up, or if the slot which is full, you haven't, or if there's a slot that's full and it's the only one you can go to, like the Wednesday morning, please fill out the query form. Jeepers, this microphone keeps cutting out. I'm giving up on it. Okay, that's a bit better. Okay, so, short story, sign up for a tutorial group or fill in the query form so that you can get slotted in, because next week we already have our first test. Okay, and we will also have on ClickUp a weekly quiz, right? A handful of people have already done it and got full marks. Well done. Okay, but it's based on this week's work, right, to be completed early next week. And this will happen every week. You will have a quiz on ClickUp to complete. So don't miss those. They will count towards your semester mark. Okay, so I think that is most of the admin out of the way, and we can actually start talking about analysis. Well, first question is, well, what on earth is analysis all about? Okay, we'll talk a little bit about that, but you might also notice we even have a video on that Dr. Kikianti, thankfully, made for us. So go and have a look at that. Nice 20-minute video answering the question, what is analysis and what is it about? Okay, the short version is, well, it's about infinite processes. Okay, and at the center is probably the limit, right? Which is going to infinity, getting closer and closer to something as something gets closer and closer. That kind of a process is at the heart of analysis. Okay, so we will be covering many things that you've probably already seen. Okay, like integrals we'll get to. You know integrals, you've worked with them. Okay, we'll look at limits again. We'll look at series, sequences, and we'll even look a little bit more closely at the real numbers, right? So most of these objects are things that you are familiar with, right? And, well, we want to dig a little deeper into the core of them, right? You've applied these tools safely, but we want to see, well, why do they work? When do they not work? Okay? Of analysis, at least where it started, if you go and read the nice first 15 pages of your textbook, is coming from trying to find a good foundation to do calculus with, right? We didn't start by having a solid foundation with calculus. No, people had an idea. They tried it out. Hey, this thing seems to be working. Let's just apply it everywhere. But then, oh dear, what's gone wrong, right? In order to know what's gone wrong, we need to understand more properly exactly how do we build up this machinery. Okay, so that's our main purpose in this course. Okay, so why do analysis? Well, as I've said, main point is to get a good, rigorous foundation for calculus. Okay? And we want a deeper understanding of these objects. You've seen these objects, but we want to go a bit deeper. Make sure we've got them on a solid foundation. Okay? We'll also develop a little bit more your analytic skills and your skills of thinking in abstract thinking. So, for instance, when we start next week studying the real numbers, we will go back to questions like this. Can we prove that 0 times x is 0? Does that work? What is the foundation on which we build the fact that 0 times x is 0? If we take minus 1 in times x, we should get minus x. Now, by minus x, we mean something very special. We mean that very special number that when we add it to x, we get minus 1 and multiply it with x. Do we get that special number? Okay, so these seem like jeepers, but that's obvious. I mean, 0 times x. Come on, that's 0, certainly. Right? Well, not necessarily. Depends on what number system you're working with. Right? So we're going to be very careful to say, well, these are exactly the properties from which we can build the real numbers to be sure. Okay, so why bother? Well, let's look at one or two examples. Right? Nice geometric series that you should probably be quite familiar with, right? We want to add the numbers 1, a half, a quarter, an eighth, a 16th, on and on and on. Right? We've got quite a simple way of doing that. The good idea is to multiply it by 2. Right? That will be 2 plus 1 plus a half plus a quarter plus an eighth, and on and on and on. Why is this useful? Because now we can take, right, minus s, and what will we get? Well, the 1 will cancel with the 1. The half will cancel with the half. The quarter will cancel with the quarter. So all we'll be left with is the 2. Right? So that should be 2. Or in other words, s is 2. Right? So now we can add all those numbers up to infinity. Right? We just make this little. Okay. Let's look at another problem. Let's add 1 plus 2 plus 4 plus 8 plus 16, on and on. The same thinking. Let's multiply by 2. 2s. That's going to be 2 plus 4 plus 8 plus 16 plus 32. Right? We make our same little manipulation. We take 2s minus s. Right? Cancel, the 4's cancel. We'll be left with minus 1. So in other words, 2s minus s is s. S is minus 1. Does this seem like a... getting bigger? We get to minus 1. What on earth happened? This is why clearly something's wrong there, seriously wrong. Okay, so we need to make sure when we're dealing with these kinds of objects, we know what are the rules we can apply. Why is it, first case, it seems to work, but when we get nonsense, right? What are the... Okay, let's look at another one. Okay, take the limit as n goes to infinity of the sum of 1 over n times. Okay? So infinity of 1 over n plus 1 over n plus 1 over n plus 1 over n. If we add 1 over n times, what are we going to get? Right? We'll just get n times 1 over n. So that is limit n to infinity of 1. Limit of a constant 1 is just 1. Okay, good answer. went about it in a different way. So let's go back to limit n to infinity, 1 over n plus 1 over n plus 1 over n. Right? We've got some nice limit laws we studied. We know if we have the limit of a sum, that's the sum of the limits. No problem. Right? This should just be limit n to infinity of 1 over n plus limit n to infinity of 1 over n. Right? N times limit n to infinity of 1 over n. But limit as n goes to infinity of 1 over n is just 0. So we have 0 plus 0 plus 0, which should be 0. So thus, we conclude that 0 must be 1. Something went wrong again. The whole point about analysis, these things that you know about, but looking very carefully at the foundation and building it step by step with logic to make sure that we don't somewhere do something illegal. Or even more importantly, when you get a strange answer, you have the tools to work out what went wrong. Right? Why doesn't it work? Right? Why didn't it work? Can I prove that it doesn't work? If you can't prove that it doesn't work, then you go back to trying to prove that it does work. And you go flip-flopping between the two until finally you reach an answer. Okay. So, what are the main themes in our course? Set this all up foundationally, good logic. We need to cover this week a little bit of logic. Right? And that's what our first 2 lectures are about. Just thinking a little bit about logic and talking about that so that we have a good grounding to start with. Right? Then we'll talk about the real numbers and introduce them very carefully. In real numbers for years and years and years. But objects, right? You've seen them so much. We use them every day. Square root 2 isn't strange for you. But there was a time when square root 2 was thought don't exist. If you said that, say that. Does it fit with our get to more? Okay. We'll then get into sequences, go back to continuous functions, get okay, so that is our plan. Starting today with our foundational issues, which is the logic. Okay. So that covers section 1.1 in your textbook. Section 1.2 and 1.3. Because we expect you to have some basic understanding of sets and functions. I would advise you, go and read, go and revise, make sure your sets and functions are where they should be, because we will be needing them as we go through the course. Okay? There's also one self-study video on do in our first. That is statement happens, or there exists an X. So please, sometime this week, go and have a careful look at that. Okay, so finally, we get to the meat. Logic. So, right, is identity, right? Or, well, we made a mistake somewhere in our proof. Into its component parts, right? We make one statement there, that 1 is identical to 0. We make another statement here, that we made a mistake somewhere in our proof. And we connect those two statements with an or, right? So that statement we can break down into two statements, which is connected with an or. Statement. If we are into a 220 lecture, then we are on campus, right? So again, we have a statement. We are in a lecture, and we are on campus. And we connect these two statements with an if and a then, right? So we have component statements, right? Things that are true or false. Right? And we then connect them up with, well, we'll just call them connectives. And this could be some, right? This statement holds and this statement holds. Or an or, that statement, or that statement. Or a if that statement, then that statement. Right? So it's useful to break larger statements down into these component parts. But to do that, we need to know for sure how each of these connectives work. Okay, and this is where we use something called the truth table. Right? So let's look at the connective and say we have two statements. Statement P and so how does the statement and work? Okay, well, one way of describing it is in terms of its truth value when we combine different truth values for P and Q. Right? So if P is a true statement and Q is a true statement, what should P and Q be? It will be true, right? This one is true and that one is true, so the combination is true. Okay, but that's not the only possibility for P and Q. We need to look at all the possibilities, right? P could be true and Q could be false. Or P could be false and Q could be true. Or last possibility, they could both be false. So to fully describe how AND works, we need to put P and Q that we put into right? So we already said if P is true and Q is true, it will be false, certainly. Right? Other way around, similarly false. If they are both false, then surely the combination will be false. Okay, so that is then a truth table for the statement or the connective AND. Not the only one we have. How about OR? This is again for P and Q, right? False, false. Okay, or both are true. Is it true that one of them is true? Certainly, right? And if P is true and Q is false, that will be true. Other way around, true, both false, that's the only way we're going to get a false. So then we have a truth table for the connective OR. Now another operation we like to do in logic is negation. So be careful when you are negating something that happens. If you negate that, then it becomes that they exist. One. That they exist for all. Okay, more of this in your self-study video. Okay. Table for the negation. Okay, so the negation only takes in one statement, right? P. And P could be true or P could be false. Negation not P will be false, right? And if P is false, then its negation not P will be true. Okay. And what happens if we negate the negation? That we have it's not the case that not P. So we end up with false, flip that becomes true, true, flip that becomes false. So in fact, we just get back P. So if you apply a negation, logic. Okay. Right. So that comes to the idea of logic. Doesn't matter what P is. P and not P will have the same truth value, right? If P is true, and if P is false, false. They have the same, they say the same thing about P. Is our definition of logical equivalence, is that two statements are logically equivalent. So for whatever P is, we have the same truth value for the other statement, like not P. So let's look at an example of two statements, R and S. Okay, it's quite. Other statement S is that not P or Q must be the case. Our claim is that these two statements, right, although they look equivalent, right, that they say the same thing about P and Q when we combine things. Now, how can we go and prove this? Well, we can go back to our truth table, right? Truth table for this statement R, and we draw up a truth table for this statement S, right? We look at all the inputs for P and Q, whether they be true or false. S or we should get exactly the same outputs in our truth table, right? So if P is true and Q is false, then this will be true, maybe, only if S is false, then S must also be false. We want to draw up a truth table for R. So we need to go and look at all the possible values of truth for P and Q. So we need to fill in is true or P is false. Right? And it's possible for Q to be true or false, or true or false. Right? And not Q. Right? It just flips truth value. Okay? So we want P and not Q. Right? So we want the truth value for combining P and not Q. Okay, so first one. Not Q is false, then and is going to be false. True and true will be true, false and false will be false, false and true will be false. Okay, so now we've got the truth values for P and not Q. Or not, and we'll have our statement of. So we get true, false, true, true. Okay, so we've built a truth table for this composite statement, not P and not Q. Of P and Q, we know what the statement R's truth value is going to be. Now let's go and compare that. Okay, so we want to again go through all the possible values for P and Q. And let's do it in the same order. Right, true, true, false, false, and true, false, true, false. Okay, now our inner statement is not P. That's easy to do. That will be false, false, true, true. Right? And now we need to P and Q. Right? So let's do that. Or not P will give us true. False and false will give us false. True and true will give us true. And false and true will give us true for an OR. Okay, and now look at what we have here. We're putting the same P's and Q's in. The final output which we get for those particular P's and Q are identical. Right? So whatever P and Q is, the statement R as the statement S. Right? Their truth tables are identical. If, say, we know that statement R, statement S has to be false. Right? They have the same logical content. Any questions? I haven't seen a hand yet. We'll say then are logical equivalent. And those are of logical statements. And changing it into a logically equivalent statement. Right? So for instance, go and show that if you it's not the case that P and Q is true, well, either not Q. Okay? Now the way to prove with the truth table, right? Draw your P and Q, do the AND, do the negation. Draw the truth table, and then draw the truth. But it should also make a little bit of sense, right? Not P and Q going to be true. The negation is true, right? So, not exactly when P and Q is false. When is P and Q false? Right? We drew the truth table. It happens whenever we're true and false, or false and true, or false and false. The only case in which it's true is when both are true. So, not P when at least one of P and Q is false. But that's just the statement that P, right? Or it's not the case that. Does that? Think about these things. using this language. Now, we're not going to. I would love to do a whole semester on logic because it's a beautiful subject, but we're just going to introduce a little bit of language so that we can effectively talk. Okay, similarly, we can look at, well, what happens if we negate P or Q? Okay, so the idea is, would that be logically equivalent to So ask yourself, what P or Q? And when is P or Q going to be false? False. Okay. So this suggests to me that this should be logically equivalent to not P, that is, P is false, and not Q, the statement that Q is false. And indeed, you can go and prove this. That if you negate P or Q, that is logically equivalent to the statement and not Q. That is the whole point. So question is, if two statements are logically equivalent, can you use one instead of the other? That's the whole point about talking about logical equivalence, right? Is we have one statement, but we'd like to use it in another form, or we'd like to simplify it maybe. Larger statements, sometimes you can simplify it quite a lot to something much simpler, right? That is logically equivalent to it. Okay. To do those two for homework, right? To go and calculate and show that those are logically equivalent. To do. Okay, so what have we covered? We've covered or if you like the fancier names, conjunction, which is to manipulate statements to a certain level. But of course, we can do a little bit. Right? That's if you are in 220, then you are on. Okay. What is that logically equivalent to, maybe? What happens to its that implication is true? What does that mean? Can we simplify it? Okay. And equivalence. Right? Implication means if A, then B. But if we simultaneously have that B implies A, then we'll say those two are equivalent. So those two are two further connectors that we'll look at next time on Friday, as well as looking at how to use some of these ideas in some proof techniques, right? To start with real numbers next week. Okay, so that is it for this lecture. You can expect, right, based on this.